Hello friends, today's lecture will be, now we want to look at some other materials which are used in under some engineering applications, and these are ceramics, polymers and composites. So, it will be covered in one single lecture. Though these are very important ones, but metallic materials are the most widely used material, and these materials are used in very specific applications. So, ceramics are basically compounds between metallic and non-metallic elements with interatomic bonds having ionic or covalent character. So, for example, one of the very important ceramic material you might have come across is silicon carbide. So, in all your abrasive paper which you use for doing polishing, or you must have seen if any painter is coming to your home and he is rubbing the surface of the wall. Okay, they may not be using silicon carbide papers, but in the abrasive papers silicon carbide is one of the important ceramic which is used for abrasive application. Okay. Another class is aluminum oxide, okay, Al2O3. Sodium chloride, of course, you must have used, this is our common salt, and magnesium oxide. These are some few examples of ceramic materials. So, in this case you can see that one of the element is a metal, another element is a non-metal, and they both combine. So, either they can have a covalent bond between them, or they can have a ionic bond between them, and of course, that is what affects their mechanical property to a large extent. So, just to have some idea about their crystal structure. Okay, so, crystal consists of basically ions located at lattice sites. Okay, so, each lattice site is occupied by one type of ion, and crystal should be electrically neutral. So, in totality, if you see for any ceramic material, the main thing is that electrically it should be neutral. Okay, so, the number of ions of positive ions and negative ions should be same. And that is why you must remember when we were discussing defects also, the Frankel and Schottky defects, in both the cases we maintained the electrical neutrality in case of defects also. Okay, so, it is not like what we see in metallic material, where you just introduce a solute atom or you take out an atom to create a vacancy. Okay, here electrical neutrality has to be maintained. Okay, so, one type of crystal structure here is given for sodium chloride. Okay, and basically it consists, it looks like an FCC crystal structure. So, basically these are two FCC crystal structures combined together, one which is showing the position of sodium atom, another which is showing the position of chlorine atoms, okay, or chlorine ions in this case, or sodium ions. Okay, and you can see that for each one of the ion there is another ion present, okay, to maintain the electrical neutrality here. So, this is the sodium chloride is based on FCC structure, okay, two intervening FCC structure, one for sodium, one for chlorine, okay, and you can put them together to make a sodium chloride crystal. This is for a cesium chloride, okay, another type of structure based on another known crystal structure which is known to us, and that is based on BCC system. Okay, so, you can see one chlorine atom is at the center of this BCC cell, and there are chlorine cesium atom chlorine atom at the corners. Okay. Now, in looking at this unit cell, you might think that there is no, you cannot maintain a electrical neutrality here, but if you see the BCC position here is actually can be considered as a end position for another crystal. So, if you make another crystal here, these cesium atom can be occupying the or another unit cell where cesium atom ions are occupying this end positions, and then you can see that chlorine will become the body centered one. Okay. So, these are all interchangeable. The center atom in the body centered position okay, can become a corner position for another unit cell which you can make. So, in overall if you see, the electrical neutrality will be maintained for the whole crystal. The mechanical properties, at room temperature ceramic do not exhibit plastic deformation. So, basically they only show the elastic deformation part and then fracture, okay. And main thing is the nature of the bonding, because they have covalent or ionic bonds, okay. The dislocation cannot be introduced here, because that will bring an additional ion at the end, okay, and that will not be, we will not be able to maintain the charge neutrality there, okay. So, the deformation here is cannot be through dislocation movement, and that is why the ceramics usually fail without any plastic deformation. Although they have very high modulus, okay, elastic modulus values are very high for ceramics. The concepts of stress intensity factor, which we discussed when we were discussing fracture, okay, can be used to measure fracture strength in the case of ceramics, okay. So, because again the failure is through because of the defects which are present in the ceramic material, and in form of small cracks or any flaws, and basically when you apply any stress they propagate and your material fail. Under compressive load, ceramics show much higher strength, okay. They are able to take the compressive load very nicely, because in the compressive load your cracks do not open up, in fact you are closing them, okay. So, in ceramics can be used very nicely under compressive loading condition. So, that is why they are used where compressive loads are present. Measurement of properties, ceramics are not subjected to tensile test, okay. So, the property measure or property evaluation in case of ceramics is cannot be done through tensile test, okay. The reason is, first is the difficulty in preparation which is required to create that shape of the tensile sample, which we discussed earlier, okay, that what should be the shape of the tensile sample. Creating that kind of shape with ceramic is difficult, okay, because you cannot do machining or you cannot do any other forming process to get that shape, okay. So, first thing is how to prepare that kind of sample. The other very important one is, because for doing the tensile test, okay, we have seen that you have to grip the material, okay, and then you have to extend the material. So, since these are very brittle material, while gripping the stresses which will be imposed on the ceramics, that will be enough to break the material into pieces, okay. So, that is not possible, and during the test if any misalignment is there, okay, that is going to impose some bending loads on the sample, and it will fracture at very small strains, okay, usually 0.1 strain or so. So, that is why tensile tests are not the preferred way to find out the properties of ceramics. What we measure is the flexural strength is measured by a test called 3-point bending test, okay. And the flexural strength is the stress at fracture during this type of test, the 3-point bending test, whatever strength you get, okay, that is what is we will be calling as flexural strength. And now I will show you that how it is done. So, basically we can take a ceramic simple rod like this, and we can simply support it on the two supporting pins here, okay, and at the center we can apply a force F, okay. And this type of test are called 3-point bending test, because you are supporting the material at 2 points, and at the third point in the middle we are applying the stress, okay. So, what will happen, the material will bend under the load, okay, and if you are applying the force from the top, you will have tensile stresses here, okay, and you will have compressive stresses here, okay. So, when it fractures, the crack will propagate from will initiate and start propagating from somewhere here, and then it will go throughout the sample, and we can measure that at what force, okay, this happened, okay, and that can be used to calculate the stress it can take, okay. So, the distance between the two supporting point is we can say is L. The force which we measured using the load cell at fracture is F sub F. So, for a rectangular cross section, okay, having a dimension of B by D, okay, so B is thickness and D is width, then the equation for the flexural strength or the stress at fracture sigma Fs will be given by an expression like this, where Ff is your force at fracture, L is the length between the two supporting points, and B and D are the cross sectional dimension of the material. For circular cross section of radius r, okay, the expression will be slightly different, okay, which will be given by the expression given in the second case. Okay, so, using these values, okay, we will be able to calculate that what is the flexural strength of the material, ceramic material. So, this is what we are going to report in case of ceramics. Now, next is polymers. Okay. What do we mean by polymers? The natural polymer which you must have come across can be wood is one of the polymer, okay, rubber is another polymer, cotton, wool, leather. So, these are all natural polymers available to the mankind. Okay. Then there are synthetic polymers which are made by men, okay, for their use. Okay, and this polymer actually consists of hydrogen and carbon atom. Usually there are some other elements also, or some other atoms also can be added in the molecule. Okay, but usually most of the polymer, the main component will be hydrogen and carbon atoms, and the bond between the hydrogen and carbon atom will be covalent type. Okay, so it will be like this: carbon atom is sharing each carbon atom is sharing one electron with each of the hydrogen atom, okay, so that they have a stable configuration. So, in this case it is methane when it is sharing with 4 hydrogen atoms. Okay. If you combine two carbon atoms and remaining are shared by the other hydrogen atom, then it is ethane. Okay. If we do not have the 6 hydrogen atom, then there has to be a double bond between the 2 carbon atoms. Okay. In that case it is called ethylene. Okay. So, you can have different types of molecules, okay, which can be used to make a polymer by having different type of bonds between the carbon and hydrogen atoms. So, if you see the molecule of a polymer, these are called macromolecules, okay, because they are very long chained molecules. Okay. So, one molecule may consist of very large number of atoms, and it may be in like a chain form. Okay. So, molecules in polymer are macromolecules, which are basically long and flexible chains. Okay. And these long molecules consist of a small unit called mer. Okay. So, one small unit can be shown here, okay, which is basically ethylene molecule. So, this is the mer, the 2 carbon atoms and 2 hydrogen atom attached to each carbon atom. Okay. So, this is one single unit which can be repeated. So, one unit is shown here. Okay. This can be now repeated again and again, okay, to make a big chain of these small molecules, okay, and make a big molecule. So, these are repeated successively to give many mers, okay, and that is why these are called polymers. Okay. Large number, poly means more, large number. So, these are many mers which can be termed as polymers. Okay. So, this is a very popular polymer, polyethylene. Okay. So, one ethylene can be combined together to create a long chain of molecule. The chain shape and structure, if we want to see, okay, chains are not straight but in zigzag shape. Okay. So, a chain can be like this also, maybe something like this. Okay. Very long chain, and basically all these small molecules keep attaching to each other, and you can make a very long chain like that. Okay. So, these are not straight chains, but maybe arranged in a very zigzag fashion in the molecule in the overall structure. So, we can define the structure according to this. Okay. So, linear polymers are basically Mer units are joined together end to end in single chain with van der Waals forces and hydrogen bonding between chains, example polyethylene. Okay. So, basically in this case you have these long chains, okay, of macromolecules, and there may be between the carbon atoms and the hydrogen atoms, okay, there can be some van der Waals forces can be there, okay, or hydrogen bonding can be there between the two big molecules. Okay. So, you have two chains, and between the two chains there can be some kind of forces can be there. Okay. These are either van der Waals forces and or hydrogen bonding, and in both cases we know that these forces are very weak. Okay. So, it is not going to hold it very strongly, you can have some relative movement between the chains. Okay. So, these are not very strong forces, but they can keep the molecules kind of together by having a small force acting on them. Another kind of polymers can be branch polymers. Okay. In this case you can have small branches coming out of the main big chain. Okay. So, these are called branch polymers. Then you can have cross linked polymers. In this case now the two big chains are kind of connected with each other with cross linking. Okay. So, these cross linkings are there. Okay. So, adjacent long chains are joined at various locations by covalent bonds. Okay. So, and then there can be a network polymer which forms a 3-dimensional network. Okay. So, you can see that as we are going from this simple type of arrangement, okay, to a branch type and then to cross linking type and to network polymers, you can understand that the strength of the polymer will increase in this way, okay, because it will be more difficult for you to deform the polymeric chains, okay, during when you are applying any stress. Okay. Now, if you want to see in terms of crystallinity, that whether there is any crystalline nature is there for polymers, okay, the polymers can be divided into 3 types. Okay. An amorphous polymer means there is no long range arrangement of atoms, okay, like what we see in metals, that atoms are arranged in a very nice fashion according to their crystal structure. Okay. In case of amorphous polymers, there will not be any arrangement of atoms. Okay. Then there can be semi-crystalline or crystalline polymers. Okay. In this case, the atoms are arranged in a particular manner. Okay. You can have a repeated arrangement of atoms, and you can do some XRD analysis to find out the crystallinity in the polymers. So, it is possible to have a crystalline nature of polymer, that means there will be some repeated arrangement of atoms in the polymer. Okay. Now, coming to stress strain curves, okay, of polymers. Okay. The elastic deformation due to elongation of chain molecules by bond stretching and bond rotation along the direction of the applied stress. So, the elastic deformation part, if you see in the polymers, okay, it is due to the bond stretching and bond rotation along the direction of the applied stress. So, in this case also the bond stretching will be there between the two atoms. Okay. Then there can be 3 types of polymers are shown here. Okay. The polymer A is a brittle polymer. Okay. So, you can see that only the elastic part is there and then the fracture took place. Then there can be a plastic one which is shown here also. So, this is the B type here. So, it shows the elastic part here. Okay. Then you have the yielding of the polymer, and then you have the plastic deformation and the maximum stress at which the polymer will fracture. Okay. So, this is a typical polymeric stress strain curve for a polymer which shows plastic deformation. Then for one which shows very highly elastic deformation, okay, you will not see this yield stress and then the plastic part, but it will start deforming, and you can see that the the modulus is very small for these kind of polymers. Okay, so it start deforming, so very high strain is there without any corresponding increase in the stress. Okay, and when all the chains are kind of stretched, then you start seeing some deformation. Okay, in the plastic. It also may not be plastic here, it will be still in the elastic range, and then it will fracture at this point. Okay. So, this is how the typical stress strain curves will be there for different types of polymers. Okay. Now, we will come to the composite materials. So, we are not dealing in lot of details of these mechanical properties of these materials. Okay. Just trying to introduce you to different types of material, that how they behave, what is their structure. Okay. And they have, of course, in engineering application also they have usage now in different components. Okay. Then there can be another class of material which is called composite materials. So, in this basically you have two or more chemically different constituents combined macroscopically to enhance properties. Okay. So, in this case we add or we combine two different material which are chemically very different to each other. Okay, and these are macroscopically combined in a way that you can easily see that where the one constituent is there, where the other constituent is there. So, in the sense it is not you cannot compare this with the alloys where you have precipitates or maybe some other phase. Okay. Those are microscopically, at the microscopic level you have in situ reactions to make those alloys. Okay. Whereas in composites there are no in situ reaction, we kind of add two different constituents. Okay, macroscopically, means you can which you can easily manipulate and then you make a composite of two different constituents. Okay. Some of the example natural composites, if you want to see, one is wood, okay, which contains the cellulose fibers bounded by lignin matrix. Okay. So, you have two different constituents and they are coming together to make wood. Okay. Man-made concrete can be a very good example to understand. Okay. So, at one level you have a particulate composite of sand and cement. Okay. We are mixing them together, cement is a separate constituent, sand is a separate constituent. So, it can be a particulate composite. The other way of looking at it is when you make any column or beam. Okay. You add this mixture of cement and sand. Okay, and you also have reinforcement in form of steel. Okay, so this is now a composite of kind of a fiber composite can be, you can look at like as a fiber composite, that a steel bar is there and around that you have cement and sand mixture. Okay. A plywood is a very good example of composite. Okay. Several layer of wood veneer is glued together. So, if you see a plywood, if you cut it, you will see there are individual layers of wood, okay, which is pasted together. Okay. So, by making a composite like this, you can increase the strength of the wood, and these are very high strength material. Okay, and that is why they are used in a lot of different application as a structural material also. Okay. So, plywood is a very good example of composite. Similarly, the RCC, the reinforced concrete, is a very good example, okay, of composite that how the composite materials can be made. So, primarily composite consists of matrix, okay, as you can see in terms of wood, or that plywood which we were discussing, or the concrete which we were discussing. Okay, so it will contain a matrix and then it will contain a reinforcement. Okay, so the matrix is usually if you take metals or polymers, okay, it will be ductile, okay, but has low strength. Okay, so problem with the matrix is that though it is a ductile, but it has low strength. So composite, the idea of making composite is that you can combine the properties of two different material together to get enhanced property in the composites. Okay. So reinforcement can be, in this case, can be a strong reinforcement, but it will have a problem that it will be a brittle, it may have a brittle nature, though it may be strong, but it may have brittle nature. So you are combining two different set of properties here, one has a ductile nature, another has a brittle nature, it has a low strength, these have high strength. Okay. So by combining, when we have the composite, it will give you properties which will be combination of these both, and it can give you a much better mechanical properties. So there can be different type of composites. Okay. For example, this one is a carbon fiber reinforced epoxy cross ply laminate. Okay. So you can see that these are the carbon fibers. Okay, and they are arranged in a cross ply manner. So in one case the carbon fiber is in this direction, in another ply, next ply the carbon fiber is in this direction. So these are cross ply type of laminate. Okay, and carbon is there for reinforcement of the matrix. Okay. Similarly, there can be another type of composite which is called a particulate composite. Okay. Particulate means the reinforcement is in form of particles. So these are silicon carbide particles and aluminum is reinforced with that. So aluminum is a soft material, we know that it has lower strength although very good ductility. So we are adding this silicon carbide particles in aluminum to increase the strength of the composite. Okay. Then there can be this type of monofilament reinforced glass ceramics. Okay. So silicon carbide monofilaments are there, okay, in the matrix, okay, to reinforce it. So there can be different types of ceramics possible. Okay. These long fibers, maybe short fibers, or maybe particulate. Okay. So when we are going to discuss about mechanical property of ceramics, we will be concentrating on this long fiber, which are one of the most important composites. Okay. That what will be the how you can find out the strength and modulus properties of a composite by knowing the individual properties of the matrix and the fiber. So to find out that, you can use rule of mixture. The rule of mixtures can be applied to approximate the modulus and strength of a fiber reinforced composite. So if a tensile force of P is applied, okay, in the direction of the fiber, so if fibers are arranged in this manner along vertically, for example, then if I am applying the stress in the vertical direction, okay, if I assume that equistrength condition is going to be there, equistrength means when I am applying the force. Okay. So suppose this is your matrix and in this I have fibers like this, let us say I put some hedged and I am applying the stress here. Okay. So some force I am applying, let us say. So when these are going to deform, okay, so if there is there are no defects between the or there is no introduction of defect between the fiber and the matrix, and you have a very good bonding of fiber and matrix, what will happen? Both have to deform simultaneously. Okay, so after some time, suppose it deformed to this much dimension, okay, so it gets elongated in this direction, then the strain in both the matrix and the fiber will be has to be same. Okay, if I am applying a stress like this. So this is a condition called equistrain condition. So in both the constituents, the strain is same. Okay, so basically what we are trying to say here is that strain in F the fiber is equal to strain in the M, which is matrix, and that is the strain in the composite. So, all the three cases the strain is going to be same. If that is so, then I can use a rule of mixture kind of condition here, that the force P can be divided between the fiber and the matrix in this form. So, sigma F is the stress acting in the fiber. If I multiply it by the area of the fiber, okay, that will give me the force in the fiber, and similarly this is the stress in the matrix, this is the area of the matrix. If I multiply by that, then I will get the force in the matrix. So, when we are saying that this equistrain condition will be there, okay, so force will be divided between the matrix and the fiber according to their area, that whatever area they have. Okay, so force will be divided between the two constituents. Okay, so I can write an equation like this to express the force, total force on the system. Now, AC, the area of the composite will be basically area of the fiber plus area of the matrix. Okay. And in terms of volume fraction, if you want to see, I can say that the volume fraction of fiber plus volume fraction of the matrix will be equal to 1. 1 means it will be the total volume. Okay. So, in terms of fraction, if you want to see, it will be equal to 1. So, I can express this stress system here. So, if I divide P by the area of the composite, then I will get the stress on the composite. So, it will be sigma C equal to P by area of the composite, which is equal to, as equation suggests here, sigma F AF upon area of the composite plus sigma M into AM upon area of the composite. Now, the area of the fiber divided by area of the composite. Okay, if you remember again the one of the lecture where we were discussing about quantitative metallography, that the volume fraction whatever you get in the area, terms of area fraction can be considered as the volume fraction. Okay, from statistical analysis. So, area of fiber divided by total area of the composite, okay, will give me the fraction in area. Okay, and that I can say that it will be also as fraction in volume. Okay. So, this will be now sigma F into F by AC will be written as Vf here, and AM by AC will be written as Vm here. So, this is volume fraction of matrix, this is volume fraction of fibers. Okay. So, I can write a simple rule of mixture kind of equation like this to get the stress in the composite. You can in fact write for the modulus also. Modulus of the composite will be equal to modulus of the fiber into volume fraction of the fiber plus modulus of the matrix into the volume fraction of the matrix. Okay. So, I can write it for modulus also as I am writing for stress to get what will be the modulus of the composite. Okay. So, these two equations we have to kind of remember by using rule of mixture. Okay. So, depending upon what is the volume fraction of fiber, it will have that much contribution to the total composite stress or strength, and similarly what is the volume fraction of matrix, that will be contribute to the total strength of the composite. Now, if we want to see the stress strain curve in terms of composites. Okay. So, for example, for a matrix the stress strain curve is like this, okay, which is having lower strength and lower modulus and so on. The fiber is very stiff, okay, it has higher modulus, higher strength and so on, but have lower ductility. So, we can have a composite of these two to get strength in between the modulus of in between the two. Okay. So, we get a good compromise of property between the two, the matrix and the fiber. Okay. So, if you see the deformation of the composite, it can be divided into 3 stages. So, in stage 1 both fiber and matrix undergo elastic deformation, okay, up to this point. Stage 2 matrix deform plastically, but fiber deform elastically, okay. And stage 3 both matrix and fiber undergo plastic deformation. So, if the fiber is not does not exhibit any plastic deformation, for example the fiber is made of ceramics, just for an example, and it does not show any plastic deformation, then the whole deformation throughout the deformation of the composite, this will show only the elastic deformation, okay, whereas the material is showing the plastic deformation, okay. And we know that it will show the elastic deformation and then it will break, okay, though the matrix will keep on deforming plastically, okay. So, when it breaks, the crack will propagate through the ceramic, but because these fibers are surrounded by the matrix, the ductile matrix, this crack will not go beyond the matrix, okay. In the matrix the crack will be blunted, okay, it will not remain as sharp. So, by doing this kind of making a composite, what we are doing is that if any, because of defect, any one fiber breaks also, the crack is not propagating throughout the material. If the whole material is of ceramic, what will happen if a crack start propagating, it will propagate throughout the volume of the ceramic and the whole material will fracture. By making a composite, what we are doing is, if any one fiber breaks because of any defect in that, okay, the crack will be limited only to that fiber, only that fiber will break, and it will not, the crack will not propagate beyond that fiber, because around that fiber there is a ductile matrix, okay. So, if you keep on deforming the material and all the fibers will keep on breaking and the remaining material will deform plastically, what you will see after the deformation, if you do the analysis of the fracture sample, you can see that these fibers are broken in a brittle manner with a faceted kind of fracture, okay, a fracture in which the material is divided in two parts and there is a planar fracture here, and the matrix, the fiber has pulled out, okay. So, material has been deformed plastically and there is a debonding between the fiber and the matrix, okay, and the fiber are pulled out. You can see here also that fiber are pulled out of the matrix, okay. So, they deformed elastically and then they it fractured, okay, whereas the matrix deformed plastically, and later on there has to be debonding between the matrix and the fiber, okay. So, with that we have covered one class of materials, okay, that is ceramics, polymer and composites, okay, and ceramics are one of the very important ingredient of any composite, okay. Lot of composites are made using ceramics, okay, and polymers also, because they do not have very good strength, they are usually strengthened by adding some kind of fibers, okay, or any other reinforcing material, okay, to increase their strength. So, using this class of material, you can make another type of material which is composite, and that is very useful for engineering application, okay. So, thank you.